So one way that we can expand the amount of information embedded in a graph is to use what are called parametric equations or parametric functions. And so if you think of a circumstance where if you're firing a rocket, as it describes here, you have to keep track of the horizontal position of the rocket. You have to keep track of the vertical position of the rocket. So you want to know how far in the horizontal and vertical direction it's traveling. But there's also a time component that's important. If you're trying to hit a target, or if you're trying to avoid hitting something out in space as you launch a satellite, you need to make sure that you're keeping track of not just the horizontal and vertical position of the rocket, but you also need to keep track of the time it's going to be at a particular location. But in an equation where we're tracking the path of some projectile or something like that, there's only x and y variables. There's no third component. There's no time. And so that's where we can introduce this third variable called a parameter. And so that third variable is usually represented by t, since it's very often indicating or representing time. And so we call it a parameter. And so what we do then is, instead of having one equation that just has x and y in it, we instead write two equations, one for x, one for y, that are both based on t. And so as you can see in the example in front of us, we have exactly that. We've got two equations, one for x and one for y, both of them with t as the variable on the other side. And so in the x equation, we have x defined as being t squared plus 1. In the y equation, we have it defined as equaling 2t. And then oftentimes we'll have some restrictions as to what our values for t, what our inputs for t are going to be. In this case, we've restricted ourselves to just being between -2 and +2. And so now what we're going to do is we're going to use this kind of chart here, this table, to generate a set of x and y coordinates based on these various values of t. Now, one thing I'll point out is there's no reason that we can't have t be a negative number, even if it is representing time. Oftentimes we'll restrict ourselves to having t being greater than or equal to 0 or something like that, depending on the context of the problem. But here, since we don't have any kind of specific context related to anything happening in reality, we can go ahead and just use any values of t we want. Negative values don't matter. And so I'm just going to plug those values in for x and y and generate those xy coordinates. So if we plug in -2 for x, we get -2 squared is 4, plus 1 is 5. If we plug in -2 for t in the y equation, we're going to get -4. And so that means we can go to 5, -4, roughly about there. We can make a dot. And we know what the t value at that location is. So we have an xy coordinate, but embedded in that information is the fact that t equals -2. We'll go ahead and label that up when we're all done here, just so that we can get the plot of our xy graph first. If we plug in -1 for x into t or -1 for t into the x and y equations, -1 squared is 1, plus 1 is 2. -1 times 2 is -2. So I can go over 2, down 2, make a dot there. But again, the extra bit of information, besides just knowing that that point is there, is that t equals -1 at that location. If we plug in 0 for t into each of the two equations, we get 1 for x and 0 for y. If we plug in 1 for t into each of the equations, we get 2 and +2 for our y value. And then if we plug in 2 for t, we get 5 and then +4 for y. So I can go over 5 and then up to 4. So hopefully what we're seeing here as we generate these points, and we weren't restricted to just plugging in integer values, but that's what was convenient for us, is we end up with kind of a parabola type shape. Now, I'm not going to draw arrows on the ends of my parabola because of the restriction that we have for t here, that we are limited to just values between 2 and -2. But again, each point along our curve, every single one of them, not even just the ones that we plotted, has a t value associated with it. So for example, this location not only does it have the coordinate 5, -4, but as we can see from our table, we've got t equals -2 at that spot, or t equals -1 at 2, -2. This spot here, we had t equals 0. That was a result of plugging in 0 for t. Here we had t equals 1, and then t equals 2 was our last point. So it's this extra layer of information that's associated with each of these xy coordinates that we see in front of us on the graph. Now, most of our analysis of graphs and of functions is not while we have a set of parametric equations. We don't have all that much experience with them, certainly, since we've just been introduced to them. And so it can often be convenient for us to, instead of seeing the set of parametric equations, to work with the single xy equation that represents that graph. And so what we can do is we can combine the sets of parametric equations into a single, what we call Cartesian equation, xy equation, by eliminating the parameter. And so depending on what format our parametric equations are in, we have a variety of techniques that we can apply to eliminating the parameter and coming up with that one equation that's in terms of x and y. So, for example, in this one that we see here, we have x equals the square root of t, y equals 1 minus t. When I look at those parametric equations, I don't know what the graph is going to look like if I would have to plot out a series of points. I don't have a lot of experience with what the graph should end up looking like. Just like on the previous one, I didn't know that that was going to turn out to be a parabola until I plotted those points just because of my inexperience. So I'm going to eliminate the parameter, so I have to isolate t in one of these two equations. Now, we might think it's easier on the bottom one since the t isn't underneath the square root symbol, but oftentimes we want to write functions as in y equals format, where the x is then on the other side. So I'm going to leave that bottom equation as right now 1 minus t, and instead I'm going to work on this top equation here and isolate t in that one. And I can do that by squaring both sides. If I square both sides of that equation, I'm going to get x squared equals t. And so now I can make that substitution into this second equation. And so then I get 1 minus x squared. And so I can look at this equation and I know, hopefully, that the shape of that graph is going to be a parabola. It's going to be upside down. I know that the y-intercept is going to be 1. I can make a lot more judgments or predictions about what the equation is going to look like when I see it as a single Cartesian, as a single xy equation, as opposed to a set of parametric equations. Now, if I only ever had that equation there, then I wouldn't have that extra layer of information about it, of having a t value associated with each point. But I at least now can have a pretty good idea as to what the graph will look like, even if I don't have that extra piece of context and information. Now, for parametric equations that involve sine and cosine, or secant and tangent, as we see in the two examples below, using the technique that we did on the previous example, where we isolate t in one equation and substitute it into the other, I don't think it takes very long for us to realize that that's going to be a tricky proposition. If I was to try to isolate t, I'd have to take the arc cosine of t of both sides and then plug in that into the other equation, so I'd have the sine of the arc cosine of t. It would be a catastrophe. So instead we're going to have to take a different approach, and there's just a little bit of a trick to it, but once we see the trick it makes sense for us. And what we're actually going to do is we're going to put into practice here the use of one of our Pythagorean identities from our trigonometry unit. So what I'm going to do first is I'm going to isolate the trig piece in each of these two equations. So I'm going to take the first equation and divide both sides by 4. So I'm going to have x over 4 equals the cosine of t. And then in the second equation, I'm going to end up with y over 6 equals the sine of t. And so once I've got those trig pieces isolated, I'm going to square both sides. So I'm going to take each side of my equation and in both cases and square them. So I end up with cosine squared equals x squared over 4, or x over 4 squared, and sine squared equals y squared over, or y over 6 squared. And so now this is where the identity comes in, because again, we're not isolating t in order to be able to substitute. Instead, we're going to use that original Pythagorean identity. We're going to add these two equations to each other. And so on the left-hand side, we've got x squared over 16 plus y squared over 36. And on the other side, we've got cosine squared plus sine squared, which hopefully is ringing a bell for us. Cosine squared plus sine squared equals 1. And so as we look at this equation, not in this Cartesian form as opposed to as a set of parametric equations, we can see that this is the equation of an ellipse. And so what we have here is we have the set of parametric equations that will result in an ellipse that's centered at the origin, that extends 4 units in the horizontal direction at its maximum, 6 units in the vertical direction at its maximum, but also has a t value associated with each of those individual points that are on the graph. In the second example, we're going to do the same sort of thing. We're going to isolate the trig piece in each of the equations. We'll then square both sides, but obviously we're going to have to use a different Pythagorean identity to help us solve. So if we isolate the secant, we're going to get x over 5 equals the secant of t. And then in the second equation, we'll get y over 6 equals the tangent of t. And so then, like the previous one, since we're headed towards using a Pythagorean identity, we're going to square both sides of both equations. But this time we are not going to add the equations together like we did on the previous one because the identity is different. If we recall from our Pythagorean identities, we have 1 plus tangent squared equals secant squared. And so in order for me to get rid of those secants and tangents and turn it into a 1 like we did over here in the previous one, I need to isolate 1 in this identity. So I'm going to subtract tangent squared from each one. And so now I've got secant squared minus tangent squared equals 1. And so that's what I'm going to need to do here is I'm going to need to subtract these two equations in that order. It has to be secant squared minus tangent squared, which then gets me to our final result, x squared over 25 minus y squared over 36 equals 1. And so we can see that that equation is slightly different than the one that we got before. The one before ended up being the graph of an ellipse. This one, hopefully we recall that with that subtraction there, we end up with the graph of a hyperbola. So here's an example of how we can eliminate the parameter, a couple of examples of how we can eliminate the parameter in a set of parametric equations where we have these trigonometric functions in each of the equations as opposed to just a simpler isolate t and then substitute into the other.